Human beings are remarkably weak engines. Even pushing to your physical limit on a steep climb, you're outputting roughly 200 watts, barely enough power to run a few standard household bulbs. Because our biological power is so capped, bicycle engineering focuses on one question: how do you harness and multiply that tiny output? Over the last century, designers have split into two opposite camps. One tries to cheat the wind through aerodynamic complexity, while the other strips everything away for raw mechanical simplicity. Choosing a bicycle means deciding which of these two engineering philosophies solves the specific friction in your daily routine. This table compares the extremes of both approaches. On the left, human-powered vehicles like the Aerovelo Ada use a recumbent carbon shell to hit 89.6 miles per hour on just 198 watts. On the right, a classic urban single-speed tops out near 15 miles per hour using a bare steel frame and a fixed 44/16 gear ratio. That speed requires being bolted inside a 55-pound shell. You have virtually zero visibility and almost no maneuverability, making it unusable for navigating real-world city traffic. The urban single-speed takes the opposite path. By stripping away everything but the frame and one gear, you get a durable, direct power machine that thrives in tight spaces. The cost of that simplicity is your posture. Because the rider sits upright, your body acts like a sail, creating drag that places a harder carb on your top speed. Maximum aerodynamic efficiency and maximum mechanical simplicity cannot mathematically exist in the same machine. This matrix shows how bikes trade speed for maintenance. Aerodynamic efficiency is the vertical axis, mechanical simplicity the horizontal. Human-powered vehicles occupy the top left quadrant. By shrinking the rider's profile, generative design reduces aerodynamic drag to 80 times less than a modern car. This approach dominated track racing. Note the radical carbon frame and tucked position of the Lotus 108, designed specifically to minimize the rider's aerodynamic profile. That drop in wind resistance translated directly to real-world competitive success, securing Olympic gold for Britain in 1992. But pursuing that ultimate speed requires sacrificing agility and visibility while accepting massive upfront engineering costs. Moving to the bottom right, we find bikes prioritizing absolute mechanical simplicity over aerodynamics. The drivetrain is stripped to its barest components: no derailleurs, cassettes, or shift cables. It is just a chain connecting one front chainring to a rear cog. This removes almost all drivetrain friction. With fewer moving parts, the power from your legs goes directly to the rear wheel with zero mechanical loss. The compromise is that you are locked into a single gear ratio. A typical urban setup uses a 44-tooth front chainring paired with a 16-tooth rear sprocket. That ratio is fast enough for flat roads, but it makes climbing steep hills punishing and descents difficult to manage as your legs spin wildly. By stripping away the mechanical transmission, the rider becomes the transmission, forced to absorb every change in the terrain physically. These two extremes demand different materials. Reaching 90 miles per hour requires fragile carbon fiber honeycombs. Surviving city streets requires indestructible chromoly steel. Steel provides the durability commuters need: built-in mounts for racks and fenders, high weather resistance, and a natural flex that absorbs vibration on rough roads. This fixed gear design was born on the steep banking of indoor tracks. Riders navigate without brakes or multi-gear drivetrains to ensure direct power transfer. Long before we developed advanced aerodynamics, this level of mechanical simplicity was the original standard of performance. That track heritage proves that older, heavier technology often provides the specific durability required to survive a city environment. To translate these physical trade-offs into a buying decision, we can map your riding habits directly to the hardware that supports them. Consider the urban commuter. Your terrain is mostly flat, you have a limited budget, and prioritize low maintenance. A steel single-speed or a flip-flop fixie, like the Steed Thoroughbred or the Genesis Day 1, is the definitive mechanical solution for this environment. Choosing this means accepting high aerodynamic drag and relying purely on your own fitness to handle hills. Other riders cover long, flat distances and want maximum speed without the maintenance of a complex derailleur system. In this case, an aero-optimized track frame uses deep section wheels and bullhorn bars to cut through the wind efficiently. The trade-off is the loss of upright agility and the practical mounts needed for commuter racks or fenders. A 90-mile-per-hour carbon pod represents engineering perfection, but perfection is useless if you have to carry it up 3 flights of stairs every night. Physics sets the limit for top speed, but the most efficient machine is the one that successfully removes the friction from your specific environment.